Let's start with the simplest example of projectile motion, which is one-dimensional projectile motion vertically upwards, no drag, no Coriolis forces, no variations in g, no air resistance, no other forces acting at all near the surface of the Earth. So let's imagine we have a mass m, which is launched upwards at a speed v naught. First question is, what is its flight time, capital T? That is the total amount of time that it's in the air before it returns to its launch elevation. And secondly, what is its maximal height, capital H? What is the height above its launch position that it reaches before it starts to descend? Now, to do this, we're going to need our constant acceleration kinematics equations. First, we should recognize that this actually is a constant acceleration problem. So over here, I've drawn a little picture of the trajectory. Nature does not have any coordinates, so we get to choose our coordinate system as we please. Let's choose it so that we have the y direction, positive, vertically upwards. We'll choose some starting location y equals 0 as the launch height. Now, I don't know if this is being launched from the ground itself or from someone's hand above the ground, but I'm going to call that initial height of the launch y equals 0. And you're always free to do that. We've also got our v naught, the initial y velocity is directly upwards, and I've gone ahead and labeled in this y equals capital H as our maximal height before this turns back around following the dotted line. Of course, this is actually just vertically straight up and down. I've drawn it a little bit offset so that the trajectory doesn't overlap with itself on the way back. So it's important to recognize that the acceleration during this motion is constant. We have a downwards pointing gravitational acceleration, which is just g, good old 9.8 meters per second if you're on Earth. And that lets me use these constant acceleration kinematics equations. There is a fifth one, actually, that eliminates v naught, I guess, but we won't need it for this problem. In fact, only one of these kinematics equations is going to be relatively useful for this first question. So, what is its total flight time? There's actually several different ways you can go about this. Clearly, we need something involving a time, so I'm probably going to use either the first or second kinematics equation. The fourth one has a time in it, but it's missing acceleration, and I know the acceleration, so I shouldn't choose that one. It doesn't have the g that we know is supposed to be in there. In fact, it depends on my final velocity, which a priori we don't actually know what the velocity is once it returns to your hand, although by symmetry we could figure it out. Let's go ahead and use the first kinematics equation to figure out that flight time. And we're going to take advantage of the fact that at the maximal point of this trajectory, we know that the y velocity of our particle is 0. We know that because once it reaches this maximal height, it has stopped moving in the vertical direction at all, and that means it's a maximum. And maxima have 0 derivative, and the derivative being the velocity means the speed is 0 there. Okay, using that, let's write down our equation. All I've done is rewritten that first kinematics equation in the y component. At the top, we know Vy is 0. Initially, we know that V naught y is just V naught. That is indeed the initial velocity of our particle. And we know that the acceleration in the y direction is negative g. Please note that g itself is a positive number. It's the magnitude of the acceleration. It's positive 9.8 meters per second. But the acceleration component is, of course, downwards. This object will be accelerating downwards the entire time that it is moving. So we put in the minus sign there. And then for the time, well, I want to find the total flight time. Recognizing that I'm choosing this point where Vy equals 0, that's actually not the total flight time. That's just the time to get up to the top. Now, if there's no drag, by symmetry of this situation, we should have the same flight time up as we do to return. We can prove that a different way if we like, and maybe we'll do that in a second. But for now, let's just say by symmetry, this time should be half of the total flight time. So I'm going to write t over 2 for this flight time to reach this maximal point. Capital T is the total flight time, so doubling this time should give us capital T. This quickly gives us that the total flight time is 2v naught over g. And indeed, that is going to be the total flight time of this particle in the uniform gravitational field of Earth. We can check units and dimensions if we'd like. So for example, v naught has dimensions of length over time. the acceleration has dimensions of length over time squared. Dividing those out does give us a time, so at least dimensionally this checks out. It also makes sense that the bigger the launch speed, the longer it's in the air, or the stronger gravity is, the less time it's in the air, so that checks out. Let's see if we can do this another way. An alternative method would actually be to use our second kinematics equation. Here we know that when the particle returns to its position of launch, its vertical component of position, y, is 0. We also know from the way we've chosen our coordinates that its initial position of launch, y0, is also 0. We know that v0y is still v0, the launch speed. And now I'm actually tracing the trajectory all the way back to the ground, so the time I'm interested in really is the total flight time. No more dividing by 2 because I'm taking the trajectory all the way back to the ground. As before, the acceleration component in the y direction is negative g, and the time is again the total flight time. Now here we have a quadratic equation that we could solve for capital T. You don't need the quadratic formula though because there is no constant term. I just have my quadratic and linear terms, so I can factor this. If the product of two numbers is equal to 0, then one or the other product factor has to be equal to 0. We know that t is not equal to 0. The flight time is not 0. It actually does spend some time in the air. The reason we're getting this auxiliary or artifact solution is that, well, at time t equals 0, the particle is at the ground, so it does track with the actual launch trajectory of the particle. But we're more interested in this factor that's in parentheses. When that equals 0, we again get our previous result. So there's a second way that we can calculate the time. For part B, calculating the maximal height, we can again do it in a couple different ways. The easiest way is probably to use the third kinematics equation. This one is independent of time. It does involve positions, which is going to be needed for our capital H to fall in, and it does involve some accelerations and velocities that we may know. You might say, why don't we just use our information that we got in part A of how long it takes to reach the top and use the first or second, well, actually, I guess the second equation that involves positions and that time. In general, of course, this will work, but it is best to try to use a solution mechanism that doesn't rely on previous results, just in case we got part A wrong for some reason. This is good for thinking about exam taking, etc. You don't really want to rely on previously derived answers just in case there was a mistake, even if it was just algebraic. What if we forgot the factor of 2 or something? So instead, let's solve this starting from scratch using the third kinematics equation. Now, even though I've written that third kinematics equation in terms of a scalar here, it actually holds component by component, and we can derive that if we'd like. I'm going to once again use the fact that I know what the velocity is at the top of my trajectory, which is where this y equals h. There, the velocity is 0. The initial velocity in the y direction is still v0. And the acceleration in the y direction is still negative g. The height, y, at this particular point is the capital H that we're looking for. And my starting position, of course, is still 0. This gives me a simple equation to solve for capital H. All right, pretty easy. It makes sense. The units check out. Length over time quantity squared divided by length over time squared gives just one length, so that checks. It also makes sense conceptually. The faster you shoot it, the higher it goes, quadratically, interestingly. And the stronger gravity is, the lower the height will reach. Let's try calculating this another way using the time method of the previous part. So here I've written down the second kinematics equation in terms of heights and positions versus time. We know that the height that we're trying to reach is capital H. We know that the launch height is still 0. And we know that the initial velocity is still v naught. The time that we want here is not the total flight time. It's again the flight time to reach the maximum height, which is half of the total flight time. And once again, the acceleration component is minus g. Now we can use our formula that we have here for the total flight time and calculate h directly. Noticing that these two terms can be combined, I have a 1 minus a 1/2, which of course is 1/2. And we have our same result that we got before.